Okay, so this video is going through geometric series, okay? So just like we went through with arithmetic sequences and arithmetic series, same difference with geometric sequences and geometric series. Geometric sequence is a sequence of numbers where you are multiplying by something each time. So in this particular case, we are multiplying by 3 each time, and there's my sequence of numbers. A geometric series is when we are adding those numbers together, okay? So the sequence of numbers is going up by times 3 each time, but the series is when we are then adding those terms of the sequence together. All right, so your formula in the log tables for sum of a series, for a geometric series, is a times 1 minus or to the power of n over 1 minus or. Okay, a of course is the first term and or is the common ratio. All right, so let's jump straight into a couple of questions then using this. So try this question. In the geometric series 1 plus 3 plus 9 plus ... find the 10th term and the sum of the 10 terms in the series. Okay, pause the video, see how you get on with this one. So the two things that are going to help us here are, of course, the nth term of a geometric series, which is in the log tables, and of course what we have above here, the sum of the terms in geometric series. Okay, so with the 10th term, let's fill in as best we can what we're looking for here. So for the 10th term, filling in for A straight away we can see is the first term 1. Or is the common ratio. So again, by inspection, we can see what's going on each time, and we realize that we are multiplying by 3 each time. So the common ratio is 3. 10 minus 1 then is going to be 3 to the power of 9, which works out to be 19,683 is the 10th term. Okay, and it is going to escalate very quickly because when you're timesing by 3, timesing by 3, timesing by 3, each time it's going to get big very quickly and exponentially. Okay, so then the sum of those 10 terms, so let's fill in this as best we can. A, we already know, is of course the first term 1. Bracket 1 minus, or we've already figured out, is the common ratio. It's going up by 3 times 3 each time, so or is 3. To the power of n is 10. We want the sum of the 10 terms over 1 minus the common ratio 3. So just be careful putting this into the calculator now, but when you do that, we get 29,524. Okay, so try this question. If the third term of a geometric series is 32 and the sixth term is 4, find A and or and the sum of the 8 terms in the series. Okay, pause the video, see how we get on with this one. So again, the two things you have to work with here, given that we're talking about geometric series and sequences, is Tn is A or to the n minus 1, and of course the sum of the series is A times 1 minus or to the power of n over 1 minus or. Okay, and again, fill in your information as best you can. So we're talking about the third term here. So T3 is equal to A, I obviously don't know yet, nor do I know or, but I do know n is 3, so to the power of 3 minus 1, that works out to be A or to the power of 2, and that third term should result in 32. So that's as far as I can go with that. And I'm going to do the same thing for T6. So T6 is A, I don't know, or I don't know, to the power of 6 minus 1, which of course is A or to the power of 5, and the sixth term is 4. Okay, so again, I have two equations here, two unknowns, non-linear, so I'm going to get one and sub it into the other. So I'm just going to work with this one here on the left-hand side. I'll divide both sides by r squared to get the A on its own, and A is equal to 32 over r squared. I'm going to take that then and I'm going to sub it in to here. So instead of the A here, I'm going to sub in 32 over r squared times r to the power of 5. So evaluating that a bit further, I get 4 is equal to 32 or to the power of 5 over or squared. And simplifying this, or squared divides into or to the power of 5 or cubed times. So I'm left with 4 is equal to 32 or cubed. Now I can divide both sides by 32, and I'm left with or cubed is equal to 1 over 8. And therefore or is equal to the cubed root of 1 over 8, which works out to be a half. So there my common ratio is a half. So I'm going to come back then to this. If or is equal to a half, and of course a is equal to 32 over or squared, I can sub in a half in for the or, and I'm getting a is equal to 128. Okay, so the next part of the question asked for the sum of the 8 terms. So again, this is what I need. I'm going to write it out for myself. The sum of a number of terms in a geometric series. So I know my a now, and I know my or, and I want 8 terms, so n is 8. So a is 128 times 1 minus, or is a half to the power of 8, n of course is 8, all over 1 minus a half. And again, be very careful putting all of that into the calculator. It results in 255. So the sum of the 8 terms then is 255. Okay, so try this question. So we come across this sigma notation, of course, already in arithmetic series. It's now coming up, of course, in geometric series, because what we have here is the nth term of geometric sequence. And of course, our sigma notation means we want the sum of all these terms. So hence it's a geometric series question. So all we're asked to do here is just evaluate this. In other words, work this out. So if you remember, you want from the first term to the 8th term. So you want the sum of the 8 terms if the nth term is given by 2 times 3 to the power of or. Evaluate then, therefore, this notation here. Right, pause the video, see how you get on with this. So this is what I'm looking to fill in. And then I'm going to need to see what parts of this I need to work out. So obviously I'm going to need my a and I'm going to need my or. So looking at what I have here, the first term is going to be evaluated by subbing in or is equal to 1. So there's the first term, 2 times 3, which is 6. Then you'd need to add to the second term. If I was to evaluate this out the long way, the second term would be when you are subbing in or equals 2. So you end up with 2 times 3 squared, which is 2 times 9, which is 18. And then you'd carry on 2 times 3 to the power of, subbing in 3, and so on. And you could do that the long way around if you wanted, because you're only going up to 8 terms. Okay, I'm going to use it using the formula because, again, anything higher than 8 or even 8 is going to be laboursome enough. I've got all my information I need now, having evaluated the first and second term, because now I know that a is 6, and straight away I know the common ratio. In other words, what's happening each time? It's going up by times 3. So the common ratio is 3. Okay, right. So filling then in for the sum of the 8 terms, a is 6, 1 minus, common ratio is of course 3, to the power of 8 is n, over 1 minus, and or of course is 3. And then we just need to evaluate this on the calculator, be very careful. Works out to be 19,680. Okay, so the last element of geometric series that I want to cover here is the other formula that's given to you in your log tables, which is the sum to infinity of a geometric series. Okay, so here's the way it's given in your log tables. Sum to infinity is equal to a over 1 minus or. Obviously a is the first term and or is the common ratio. Now the only way this makes sense, that we're adding on an infinite amount of terms, is if the common ratio is between -1 and 1. Okay, and that is the stipulation for this formula. Because what this means is, say you have the sequence 32, 16, 8, 4, and so on and so on, okay? The common ratio, if you've spotted, is times a half, all right? A half is between -1 and 1. Because it's this fraction, then what's going to happen when I continue to multiply by a half and multiply by half and multiply by half is the series is going to get smaller and 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 smaller. And what will happen is it will tend to a particular value, okay? As it gets smaller and smaller and smaller and smaller, having, it is going to get closer and closer and closer and closer to a particular number. And because your common ratio is a fraction, and because the series as it goes forward gets smaller and smaller and smaller, that's how we can actually find out the sum of the infinite terms, because we know it's got to tend towards something. Okay, so the only way that you ever can be asked to find the sum to infinity of a particular series is if the common ratio is between -1 and 1. And another way of writing that is the modulus of r has got to be less than 1. In other words, you've got to be dealing with this kind of a fraction for a common ratio. Okay, so let's see this in action. Okay, so let's take that example that we were just talking about, and let's find the sum to infinity of this particular geometric series. Okay, pause the video and see how you go. Okay, so obviously what we're dealing with here is a over 1 minus r. This is what's in your log tables. Straight away, we can see the common ratio is times a half. So a is equal to 32 and r is equal to a half. So filling in over here then, the sum to infinity is going to be 32, which is a over 1 minus a half. And it works out to be 64, okay? So if you were to take a look at this, we obviously have 32 plus 16 plus 8 plus 4. The next value would be plus 2 and then plus 1. Well, those terms added up so far works out to be 63, and then you're adding on, of course, a half, a quarter, 1/8, and so on, and they're getting smaller and smaller and smaller and smaller and smaller and smaller. And as you continue to get smaller and smaller and smaller, this will all then, the sum of these moving forward will all then tend to 1. So we would eventually, the sum of the whole series would always just get closer and closer and closer to 64. So that is your answer. So this comes up often when you're asked to write recurring decimals as fractions. So we're going to take an example now of how we can use the sum to infinity to write recurring decimals as fractions, okay? Okay, so let's take this question. 0.23 with the recurring dots on both the 2 and the 3, write in the form a over b, where a, b are an element of the natural numbers. In other words, positive whole numbers. Okay, pause the video and see how you get on with this if you feel you've got an idea of how to approach it. If not, take a look and I'll go through it now slowly. So first of all, to get an idea of what this is, 0.23, as I said, with the recurring dots on the 2 and the 3, mean that the 2 and the 3 recur. Okay, so that's what it looks like. All right, 0.23, 23, 23, 23, and so on. And it occurs in that way. If we were to then break this up into a series, I could write it as 0.23 plus 0.0023 plus 0.000023 plus, and so on, continuing on. Okay, now that I've written it out like that, it's going to continue on, obviously, to infinity. So we're going to use the sum to infinity formula. Figure out your A, figure out your R, and fill it in and see if you can work this out now. If you want to pause the video from now. If not, we'll go through it now together. The A, the first term, is quite clearly now 0.23. The common ratio, well, what am I multiplying to that to get that? And the answer is I'm multiplying by 0.01. Okay, so the common ratio is 0.01. So that divided by that will give you 0.01. Okay, and then that multiplied by 0.01 will give you that. Okay, so just if you're wanting to double check your working out, you can do it in that way. So the common ratio is 0.01 and A is 0.23, and the formula I'm filling it into is sum to infinity A over 1 minus R, which is 0.23 over 1 minus 0.01. Okay, and doing that then on your calculator will give you 23 over 99, which is 0.232323 recurring as a fraction. Okay, try this question. 0.321 with the recurring dots on the 2 and the 1 only. Write this as a fraction. Pause the video, see how you get on with this. So what does this mean? So 0.321 with the dots on the 2 and the 1 is 0.3, and that means only the 2 and the 1 are recurring. Okay, so how can I write this as a series? Well, first of all, you've obviously got this 0.3. Let's separate that out because the only recurring bits then happen after that. So plus, then you'd have 0.021 plus 0.00021 plus 0.0000021 plus and so on. Okay, so what's happening? So again, leave this separate because really the only kind of series we're coming up with here is from 0.021 onwards. Okay, so A is 0.021, and then the common ratio, what's happening from here to here and here to here, is we're timesing by 0.01 again. In other words, this divided by this gives you 0.01. All right, so 0.01 is the multiplier each time. So the common ratio then is that. So sum to infinity, of course, is A over 1 minus R. So we're getting A is 0.021 over 1 minus 0.01. Okay, so that works out to be 7 over 330. But now don't forget, we still have this 0.3 or 3/10 that we need to add on here. So adding on 3/10 plus 7 over 330 gives you the final result of 53 over 165. And that is 0.32121212121 ... recurring as a fraction.